Hello everyone, welcome to lecture 8 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on electromagnetic properties of materials. So here is the lecture outline. We will look into the boundary conditions in the two cases when no surface charge is present, and then when there are presence of surface charges and kind densities. We will then look into the electromagnetic properties of materials, namely dielectric permittivity and magnetic permeability, that is epsilon and mu, and then we will do the classification of materials based on anisotropy, linearity, magnetization and conductivity. So, at the interface of two different medium which has got different electromagnetic properties, how the electromagnetic field components change. Okay. For that you got to understand the boundary conditions. So, here we are studying the boundary conditions with assumption that there is no surface charge. So, these boundary conditions basically describe the behavior of the electromagnetic fields, namely electric field, the electric displacement field D, okay, and the magnetic field H and the magnetic flux, okay, B, all those things, how they are interrelated, and we are considering the source free region. So, in this case the tangential components of the electric field in medium 1 and medium 2, they will be equal. So, that is two different colors showing two different medium. Here is the interface. So, the same thing applies for the magnetic field as well. The tangential component of the magnetic fields are continuous, and the normal components of the displacement fields, okay, like electric displacement field or this magnetic field displacement field, the normal components denoted by small n, n shows you the direction of the normal, okay. So, this is also continuous. So, these boundary conditions can basically be derived from Maxwell's equation, right. So, here is a quick glimpse of the Maxwell's equations. As we know, two divergence and two curl equations are there. So, we can start taking the curl equations, okay, and you can see that the tangential components are basically obtained as curl of that electric field vector or the magnetic field vector with the normal vector, right. So, it is like n cap curl of E, okay, that way you can calculate. So, this is how you can write the tangential components, and the tangential components of the electric and magnetic fields are continuous across the interface. Now, from the divergence equation you can see the other two, that you take the component of this displacement field along the direction of the normal, okay, and that you can find out as n cap dot d1 will be equal to n cap dot d2. Similarly, it will be applicable for the magnetic field or magnetic flux density as well. So, you can write n cap dot b1 will be equal to n cap dot b2, right. So, the first two, the tangential components are coming from the curl equations, the divergence equation giving you the other two boundary conditions, right. So, that is what these are the takeaway message, that the tangential components of electric and magnetic field must be continuous across an interface, whereas the normal components of D and B should be continuous, right. So, that we have done when the boundary conditions were obtained when no surface charge was present. Now, let us consider the case when surface charge and kind density are present, and we will see that this particular concept will have a lot of practical usage, okay. And it is often convenient, in particular mathematically, okay, to define regions where electric and magnetic fields are 0, okay. So, let us assume here that there is a plane boundary surface, that is z equals 0, this particular plane, as you can see, which is basically separating your two regions, region 1 and region 2, okay. And we can derive the boundary condition for the magnetic field H by placing a small pillbox, okay, which is basically having a width of delta x, length of delta y, and the height is like delta z. So, you can see half of delta z is on the on region 1 side, okay, and another half will be below, that will be in region 2, right. The media occupying these regions are called perfect conductors, which are basically idealization of media where the field inside will be very small or vanishingly small. Now, let us assume that region 2 has got no charge or anything. So, you can safely assume that E2 equals H2 equals B2 equals D2, all are 0. So, all the fields in region 2 are basically 0. Now, the electric charges and currents are located where then? They are basically located in a very thin layer on the surface of the perfect conductor, and the surface of the perfect conductor, we can assume that the conductivity rho is we can assume that rho is infinite, okay, and when it is contained in a 0 thickness. So, let us define the surface charge density. So, you can see that rho s can be written as rho times delta z when z tends to 0, and it has got a unit of coulomb per meter square. So, that is basically your surface charge density, okay. And as we already know that d2 is 0. So, we can safely write that n cap dot d1 will be equal to this surface charge density, right. So, you can see that the difference between the electric displacement field components normal to the boundary is basically equal to the surface charge density that is available at the boundary surface. So, this is basically showing you the difference of the two D field components. D2 is 0, so we do not need to write it again, but the difference is basically the surface charge density that is at the boundary surface. Now, if you assume that Jx and Jy, these are basically current densities, surface current densities, okay, to be infinite, to create a surface current density Js when you have this thickness going to 0. So, how does it look like? So, Js can be defined as limit when z tends to 0, and you have J delta z, and this is J is like very high, okay. So, that way this is a formal definition of the surface current density, and then you can write that the tangential component of the magnetic field, okay, will be equal to that particular surface current density, because on the other side H2 is 0. So, here again you can say that the discontinuity in the tangential component of the magnetic field, or you can say the difference between the tangential components of the magnetic field is basically equal to the surface current that is available at the or flowing through the boundary surface. So, finally, we can put all the equations from the boundary conditions together in the presence of surface charge and current density, and this is how it looks like in the vector form. So, you can write n cap directly, or you can write E n cap. Okay, this is also, I am just showing you a different notation, because in different books you may find directly n cap, or it may be also written like this, unit vector along that n, which is the surface normal. So, the same thing. In few books you will see the electric field vector will be shown as bold, E in bold. Okay. Here I have shown the other notation, they may come also with the vector sign, the arrow on the top. Okay. So, that they are all similar. So, you can see that this is how it is written. So, it means the tangential component of the electric field is 0. Okay. The difference between the two is 0, that means it is continuous. Okay. Here also you can see that the discontinuity that you see between the tangential magnetic field is basically because of the surface current. Okay. So, if there is no surface current, there will be no discontinuity in the tangential magnetic field. Similarly, the discontinuity in the normal electric flux density or electric flux will be same as the surface charge density. So, this one in the scalar form you can simply write dn1 minus dn2, that will be equal to sigma rho s. okay, not sigma, rho s. And the normal component of the B field, which is basically the magnetic displacement field or the magnetic flux density, okay, that is continuous. So, it is the difference is 0. So, easy way to remember is that when the difference comes out to be 0, they are basically continuous. Now, because of the presence of surface current density, the magnetic field, the tangential magnetic field will be discontinuous, and also because of the surface charge density, the normal component of the electric flux density will be discontinuous. So, now let us look into the electromagnetic properties of material, and we will see in like there are three main properties. One is the electric permittivity, magnetic permeability mu, and electric conductivity sigma. Okay. So, epsilon, mu and sigma, these three are very important parameters, and from the electric response you will see that dielectric permittivity is basically a property that characterizes the degree of electric polarization in a material under the influence of an external electric field. Similarly, the magnetic response is given by this equation, which is P equals mu h. So, mu basically tells you the permeability. It means how well a medium can store magnetic energy, and then conductivity sigma tells you that how much the current density will be in the presence of an electric field. So, that is basically Ohm's law. So, these are collectively known as constitutive relations, because this is how the matter reacts to your electromagnetic field. So, let us first define electric permittivity. Dielectric permittivity is basically a measure of how well a medium can store electric energy. So, it can be thought of as a measure of how much interaction an electric field is basically having with the medium it resides in. And how to quantify it? So, the permittivity is basically defined as a ratio between the electric field E within a material and the corresponding electric displacement. So, you can write D equals epsilon naught E, right. So, that is basically in vacuum, right. So, we will see how we can do it for the material. So, when exposed to an electric field, bound electrical charges of the opposite sign will try to separate like this. Okay. So, they separate from one another, and the extent of this separation of the electrical charges within a material is represented by the electric polarization P. So, this is the case of a non-polarized material, non-polarized because there is no external electric field. So, the polarization is 0, overall electric displacement is also 0, but then if you have some external electric field, okay, you will see that the polarization is taking place. So, the displacement can then be written as D equals epsilon E, and because of this polarization, it can be written as P equals epsilon minus epsilon naught into E. So, how do you get this? You can straight away look from here that the electric field, electric displacement and the polarization, they are basically related by this. So, normally you have this one, okay, when the so this is without the material, okay, but then when the material is present, this extra term adds up. Okay. So, the electric field, electric displacement and the electric polarization are related by this following equation. So, you can write D equals epsilon naught E plus P. So, this is where the response of the material is getting into the picture. So, as you see that P is basically epsilon minus epsilon naught into E. So, when you put it here, you see it only remains to be D equals epsilon naught E. So, what is this epsilon? It is basically the permittivity. So, that tells you the ratio between the displacement and the electric field. Now, let us look into this constitutive relations in different types of medium. So, let us consider the most idealized one, that is linear, homogeneous and isotropic medium. So, what are these terms? Linear, homogeneous and isotropic. Linear medium means where the properties of the material do not depend on the strength of the field. Okay, so you can see that there the polarization is basically linearly proportional to the electric field. So P equals epsilon naught chi E. Okay, that's also you can write that. So chi is called the electric susceptibility. So how you can express your displacement field from here? So D can be written as epsilon naught E plus P. So P you can replace as this particular equation, epsilon naught chi E. Chi is, as I told, electric susceptibility. So you can take epsilon naught common, you get 1 plus chi. So this 1 plus chi is nothing but your epsilon r, the relative permittivity that we all know. Okay, so D can be written as epsilon naught epsilon r E, and these two epsilons multiplying giving you that epsilon that you saw in the previous slide. So it is very handy to know what is this epsilon naught. So always remember that epsilon gives you the permittivity, epsilon naught is the vacuum permittivity, and epsilon r is nothing but the relative permittivity with respect to vacuum. Similarly, let us look into magnetic permeability, which is giving you another constitutive relationship. It tells you how well a medium can store magnetic energy. So here obviously when you are exposing an applied magnetic field to your medium, the collection of individual magnetic dipole moments within most material will attempt to reorient themselves according to the direction of the field. So this particular act basically generates induced magnetism, which contributes towards the net magnetic flux density inside the material. And the degree in which the induced magnetization would impact the magnetic flux density depends on this material's magnetic permeability. So let us see how it is done or how it is expressed mathematically. So a more formal definition would be like, say, magnetic permeability defines the ratio between the magnetic flux density B within a material and the intensity of the applied magnetic field H, provided the fields are sufficiently weak. So what does it mean? That when you have B equals mu H plus mu naught M. So what is M? M is basically magnetization. Okay, and in most materials you will see that this is not happening. Okay, so you take non-magnetic materials, but then if there is magnetization happening, this overall thing you can express in terms of H and then mu. So this mu is basically the permeability, which is again mu naught and mu r. So you can think of vacuum permeability times the relative permeability, giving you the actual permeability of the material. So this is the permeability of free space. I am sure you all know this. And then last one in this constitutive relationship, important parameter is conductivity, that gives you the degree to which the material conducts electricity, right. So when an electric field is applied to the material, free charges within the material will experience an electrical, or you can say Coulomb force, and this force will cause the free charges to move through the material along the direction of the applied field, that is electrical current, right. So you see the field is this way, so your positive charges are moving along the direction, and that will be the direction of the current flow. Electrons will basically move in the opposite direction, and the reverse of their movement will give you the current flow, right. So the current is basically in this area. So J is the current density. If this cross sectional area is A, if you multiply J and A, you get the current, right. So the ease at which, or we can say how easily the electrical charges can move through the material under the influence of an electric field basically depends on the material's electric conductivity, right. So electrical conductivity, the sigma, can be defined as a ratio of the current density within a material and the applied electric field. So that's Ohm's law, J equals sigma E. So sigma is basically J by E, right. So you can correlate this conductivity with the resistivity also. So that's 1 by rho. Okay. So in many cases the electrical properties of the materials are also characterized by their electrical resistivity. So, that is why we are showing the both here. Conductivity and resistivity are just reciprocal of each other. Okay. So, that is easy to correlate. Now, next we understood the basic electromagnetic properties, their constitutive relations, and now we will move on to how do you find the velocity of the EM waves. So, velocity can be found by comparing these equations. Okay. We have seen these wave equations. Okay. So, del square E was given as mu naught epsilon naught epsilon r times dou square E by dot E square, and then you can compare this also with this form. Okay. So, where this part, these three variables are basically represented as 1 over v square. So, that means 1 over v square equals this. Okay. So, you can just break the fraction and see that 1 over mu naught epsilon naught, that is nothing but c naught square. Okay. C naught is the speed of light in vacuum, and 1 by epsilon r remains there. So, this is the typical relationship of the velocity with speed of light and permittivity, right. So, if you take, you can write v equals c naught by square root of epsilon r, that is also fine, and square root of epsilon r, if epsilon r is a real quantity, that will give you the refractive index, and that is how in the optical field people work with refractive index in most cases, right. So, these are the typical values that we all know. So, as I mentioned, refractive index is a very important term that defines a material property that tells you the speed of light in that particular medium. So, refractive index can be defined as c over v. C is the speed of light in vacuum divided by the speed of light in that particular medium, that comes out to be square root of epsilon r, which is also related to the electrical susceptibility of the material by square root of 1 plus chi. So, you are just writing epsilon r as 1 plus chi. Okay. So, now we will see how the materials can be classified based on different electromagnetic properties. So, we will start the classification with anisotropy. So, the first thing you should know that what are the isotropic ones. So, we have seen that in isotropic the properties are basically independent of the directions of the field, right. So, you can write D equals epsilon E, B equals mu H, J equals sigma E. So, all the ones with the arrows are basically the vectors. Okay. So, here because it is isotropic, so you understand that here E and D are basically parallel, similarly H and B are also parallel. Okay. But if it is anisotropic, that means the properties are basically dependent on the direction of the fields. That means in this particular case you cannot say that the electric field and the electric displacement are basically parallel to each other. Similarly, they are also not, because the material property is now direction dependent. So, a medium is a electrically anisotropic if it is described by the permittivity tensor, as you can see here, okay, and a scalar permeability mu. On the other hand, you can understand that if a medium is called magnetically anisotropic, that means for permeability it has got a tensor, which means the permeability is different along different direction, but then the electrical properties are same. So, you can just go with scalar permittivity. Okay. So, that way you can do the classification. So, this is also another notation. So, for anisotropic the constitutive relationships will be written as D equals epsilon double bar. So, that tells you the tensor, okay, E. So, this you see this notation tells you that these are basically vector fields. Okay. So, I am just showing you the different notations in different slides to tell you that all these notations are possible in textbooks. Different authors follow different versions, okay, notations, and you can write B equals mu H. So, mu is again a tensor in this case. So, here we understood that the properties are basically direction dependent, right. Now, when the properties are independent of the direction of the fields, crystals are basically described in general by symmetric permittivity tensors. there always exists a coordinate transformation that can transform a symmetric matrix into a diagonal matrix, okay, and this coordinate system will then be called as the principal system. So, what you can see that this particular tensor can be diagonalized like this, okay. So, you can just have epsilon x, epsilon y and epsilon z to make life simple, okay. The three coordinate axes are referred to as the principal axis of the crystal. So, here you can see the principal axis of the crystal epsilon can be written as this. So, if you take a cubic crystal where x, y and z are all equal, that means Ex, epsilon y and epsilon z will be equal, and that becomes isotropic, okay. However, if you go for other types of crystals like tetragonal, hexagonal or rhombohedral, 2 out of 3 parameters will be equal. So, any of these 2 will be equal, the third one will be different. So, those kind of crystals are called uniaxial crystals, okay. So, in uniaxial crystal the permittivity tensor will look like this. So, that say epsilon x and epsilon y are equal, and you can just represent them as epsilon. The third one is epsilon z, okay, that is different. Now, depending on whether epsilon z is larger than epsilon or smaller, okay. So, if it is larger you call it positive uniaxial, if it is smaller you call it negative uniaxial. So, these are different type of classifications, and there are materials also where all three crystallographic axes are different. So, you call them biaxial, okay, and the examples are orthorhombic, monoclinic, triclinic crystals, okay. So, this is where you got to remember that when epsilon x not equal to epsilon y not equal to epsilon z, that is when your medium is biaxial. So, next we will look into the classification of materials by linearity. So, as I told earlier that for the linear case, the electric polarization is basically linearly proportional to electric field. So, you can see P equals epsilon naught chi E. So, chi is basically the electric susceptibility, and you will see that the displacement is written as epsilon at E plus P, which boils down to epsilon naught epsilon r into E, right. And if you consider non-linear, in that case the properties basically depend on the intensity of the field, okay. On the other case, in the linear case, they do not depend on the intensity or strength of the field. So, you can see in a nonlinear medium, the electromagnetic response can be defined by expressing the polarization as a power series of the field strength E. So, how it looks like? So, epsilon naught chi 1 E t, and then you will have chi 2 or chi square term, which is proportional, which is depending on E square, that is the intensity. There will be chi 3 term also coming into with picture, which will be depending on the cube of the electric field and so on. So, that way you can express the polarization as a power series. So, all these quantities chi square and chi cube, these are basically the second and the third order nonlinear optical susceptibilities, right. We can also classify materials by magnetization. There are magnetic materials, and we have seen that the constitutive relations for magnetic materials look like this: B equals mu naught H plus mu naught M. So, you can write them as mu naught mu H, okay. Now, a magnetic material can be called diamagnetic if your mu is less than mu naught. That means you are getting a relative permeability which is calculated as mu r as a ratio of mu over mu naught, you are getting this as less than 1. So, if you take example of bismuth, copper, zinc, etc., they are basically this kind of material. So, diamagnetism is basically caused by induced magnetic moments that tend to oppose the externally applied magnetic field. When a diamagnetic material is basically placed in magnetic field, the external field is partially repelled, or you can say expelled, okay. So, that way the magnetic flux density basically reduces, okay. You have paramagnetic, which is completely opposite case. So, you have relative permeability greater than 1. Example of such materials are manganese, aluminum, chromium, platinum, etc. So paramagnetism is due to alignment of the magnetic moments. So you have in a paramagnetic medium such as platinum, when you are placing it in a magnetic field, it becomes slightly magnetized in the direction of the external field. And then you have ferromagnetic. So if your mu r is not constant and it is very large, something like iron, nickel, cobalt, etc. So ferromagnetic materials such as iron, they do not have constant relative permittivity, permeability. As the magnetizing field increases, their relative permeability also increases, and then it reaches a maximum, and then after that it decreases. So these are three different types of materials based on magnetization. Similarly, you can also classify materials based on conductivity. I am sure all of you know this, right? Because the relative based on the relative values of the electrical conductivity or resistivity, you can broadly classify solids as metals. They possess very low resistivity, that means conductivity is very high, sigma much greater than 1. You have semiconductors which have conductivity intermediate to metal, and insulators have very low conductivity. And here is a chart that gives you a complete comparison between the orders of values with respect to conductor, semiconductor and insulator. That is the resistivity. Okay, you can see insulators are highly resistive. Conductivity 10⁻⁶ to 8 mho per meter. Okay, mho is inverse of ohm. Okay. Then you have temperature coefficient, positive for conductor, other two negative. Okay. That means with temperature increase, the resistance will increase. Okay. Then you have current, which is coming from free electrons. In semiconductors, they are from both electrons and holes, and insulator no currents. These are the band gap. As you can see, conductors 0, semiconductor can be between 0 and 1 electron volt typically, and insulators way below, way much above. So it's like more than 6 eV. These are the typical examples. So altogether, here we wanted to discuss the different kind of classification of materials that will be interacting with the electromagnetic field. So this is not something very new, but these are just fundamentals to brush up your old knowledge about different electromagnetic properties and their classifications. So with that, we conclude here, and we will be continuing in the next lecture. And if you have got any doubt regarding this one, contact me at this particular email address. Thank you.